Okay, welcome to the fifth lecture of EECE574, the probability and random processes for graduate students. Quiz 1 is coming, so we will take it on next Thursday, not this Thursday, during the class meeting hour. It covers up to next Tuesday's material, and it will take up 10% of the total 100% as posted in the syllabus. And it's a kind of open everything quiz, but no communication with human being is possible. So it's not allowed. Your discussion among yours, not allowed. Discussion with your father, mother, friend, it's not allowed. You can use any material, MATLAB, or even if you can use ChatGPT, Bing, or Gemini. However, you cannot interact with any human being. Got it? You cannot post it on the Quora and saying that, oh, no, I didn't interact with a human being. That's the interaction with a human being. Okay, so no communication with other persons for any assistance. Homework 3 will be posted and due will be Thursday, as it is a habit in this year's course. Handout for chapter 3 is uploaded and updated. So if you have an old version of last week, please update it. Actually, this morning I updated it, but only corrected one word. So if you did it around 15 minutes before today's class, it's okay. Messages from instructor, there will be more messages, but I want to emphasize that as a graduate student, it's very important to have two principles in any problem solving, whether it is your professional problem solving or your personal problem solving, okay? Even in your personal problem solving, whenever you have very complicated problem, try to simplify, keeping the essence of the problem. Sometimes some essence needs to be removed to make the problem simple. What is important is that you admit the limitation of each simplified model. Then it's okay. The problem of some people who exercises these two principles is that they kind of believe sometimes they deceive themselves that simplified version is the true problem. It's not, okay? So whenever you have a simplification, never forget that it's a simplified version or a toy problem. Anyway, and then next thing is not only for the communication with other persons, because technical communication requires some kinds of visualization. You either need equation or figure, block diagram or something like that. However, it is also very useful for your communication with yourself. For example, suppose you have just given a research paper as a first semester graduate student. You are not yet familiar with reading papers very fast, but your boss, your advisor, or your boss in the lab gave you 20 papers and asked you to read by the end of this weekend. Probably it's not easy just to finish reading abstracts and conclusions. Whenever you do that, try to put some memo. These days, we have a lot of tablets so that you can write on it. You can easily delete whether you didn't make the remark very clean and neat, but try to leave any remark whenever you read. For example, you read some paragraph. You cannot understand. Put a big question mark there. You skipped some paragraph because it seems it's not that important, and then you just draw and mark like this so that you know afterwards, in 2 months, for example, you skipped reading that part, something like that. So you try to establish a system of visualization when you read papers. Got it? So, for example, according to my 20 years of experience as a professor, if I find a new graduate student after 1 year still read paper without having a pen on his or her hand, then I really got disappointed and can highly likely predict his or her future as a graduate student. Okay. If he or she is not a genius of genius, he or she definitely need pen or pencil whenever reading a paper or a document. Got it? So try to put a lot of marks, okay? And put a lot of remarks so that you can communicate with yourself in 2 months, in a year, in 2 years. Got it? Anyway, okay, here goes the overview of this course. So we are quickly reviewing the undergraduate material. These chapters are from the Peebles undergraduate textbook I used for teaching EC 302. In this semester, the course is also taught, and many of your friends probably is attending that course because they believe they lack of some undergraduate material. But the professor decided to change the textbook, so they use different book. So if the time does not conflict, it's still okay if you have time to attend or audit that course so that you have a diverse view of the same topic taught by different professors. Got it? Anyway, so we have just finished the probability part and random variables part very quickly during last 2 weeks. This week, we are going to cover operations on one random variable, expectation and transformation, and possibly multiple random variables. I'm not sure we can cover up to the 5th chapter. I originally planned to cover that one, but I'm not sure. I lost the confidence. It seems I'm talking too much. Anyway, let's review last week's material. So we started to learn what is a random variable. And of course, this is not a good classification method. This is not the perfect, the ultimate classification method. We usually do this. There are groups of discrete random variables. There is a group of continuous random variables, or mixed random variables, and some called singular. We have no interest. Of course, here what I want to emphasize is that as a professional or would-be professional, you have to have some way of classification on some topic. Okay, it cannot be perfect. Your classification method cannot be perfect. However, it's always better to have a classification method than have none. Okay, what is important is that you admit the imperfectness of that classification method. Got it? For example, when I teach statistical inference course, usually named estimation and detection theory in old-fashioned, old school electrical engineering, or in modern terms, classification or regression as in AI course, what I do is that I classify any inference problem in either a detection problem or an estimation problem. And also, I check whether our parameter to be detected or estimated is a random or not. Okay? And then I divide further by checking whether the observable or our observation is a scalar or vector, matrix, waveform, sequence, something like that. By doing that, I could cover almost every important topic in the statistical inference problem, and I taught the course 645 that is unfortunately have not been offered these days. However, if you have interest in that course, you can also go to my YouTube channel and also go to my teaching website or from my lab, and you can download all the material and you can study. Anyway, so after we define a random variable as what? As a measurable function. So given the probability space consisting of sample space, event space, and probability measure, what we do is that we define a mapping from the sample space to a real number. Okay, so by using the block diagram, here goes a random experiment mathematically modeled by this triplet, and here goes the outcome, and here is a mapping node called X, and of course the output is X of S. Okay. In our undergraduate courses, we just put these two together and said that we are given a random experiment that has real valued outcome. However, to precisely mathematically model what is a random variable, we prefer this two box mode. Got it? So what is a random variable? It's a function. Okay. And then we had the idea of induced probability measure, saying the sample space is the entire real number. Here goes the Borel sigma algebra, and here is the induced probability measure. One thing interesting is that the argument of this induced probability measure must be an element of this Borel sigma algebra, and such a set event is called a Borel set. Okay, for example, any interval can be a Borel set. Any semi-open interval is also a Borel set. What is interesting is that this complicated looking induced probability measure needs to just be evaluated for each semi-closed, semi-infinite interval. And this is what we call the CDF of the random variable. And also we can write it this way. Or in terms of the original probability measure, we may say that it must be X. The CDF is defined as the probability of the event that X of S less than or equal to X. Got it? So CDF is one of the most important thing because this can be common for every real random variable. That's why in our undergraduate course, we almost never talked about sample space and event space for random variable. We just handled CDF, PDF, PMF. Especially, we were interested in discrete and continuous random variables. We just used probability mass function and probability density functions in our undergraduate study. And even some courses do not much focus on CDF. As in my latte high school probability and statistics, they usually talked about CDF. So it was quite interesting. When I first took the entrance exam in 1988, December, there was one question in math section. And it was just simply talking about CDF over Gaussian random variable. So as far as undergraduates or graduates are concerned in electrical engineering, the problem was so simple. However, at that time, in our high school math, rarely touched CDF. So the notion of the function CDF defined as probability of capital X less than or equal to lowercase x, that was stunning to most of the examinees, including me. So something like that. However, what is the key? CDF. Because CDF applies to every random variable. Anyway, to have a better connection with our intuition, I also introduced two notions. One is a scatter plot. So as I emphasized, one of the important commonality between a scientific experiment and random experiment could be repeatability. So when we repeat random experiment, we can view the entire repeated experiment as a combined experiment or sequential experiment, as already I explained. And where we may combine these sub-experiments independently. So let's consider that. Then what do you have? Given a random experiment, you generate outcomes independently many, many times. Then if the outcome is a real number, you can put each realization, instantiation as a dot on a straight line, right? And then that is called what? A scatter plot, especially one-dimensional scatter plot. Given the one-dimensional scatter plot, visually or in a table form, tabular form, you can then proceed to plot a histogram. According to the precise definition, it's complicated. It's not easy. For example, MathWorks guys, the MATLAB guys, initially just devised their way to define histogram. And the command was hist. And now it is not used because many statisticians challenge that is not following the definition widely accepted in statistics. So they made a new command, histogram. Okay. So whenever you use a hist, then you get a warning. This function is no longer supported. Consult histogram, blah, blah, blah. And then when you choose a bin, since each bin over histogram is an interval, you have to decide whether you include the left endpoint or right endpoint. What do you think? What have you been taught? Which one is included? So take a look at that, okay? I will not talk about that in this course. I talked about it in our undergraduate program. You can just type in a MATLAB histogram, and then you read the documents whether left endpoint is included or right endpoint is included. Anyway, after you plot the histogram, as you can see from MathWorks document, you can normalize the histogram in some way. So the first thing is that you just keep the bin and ignore the bin width. Just you scale the height by dividing each height by the total number of instantiation. For example, you generated 100 samples, then probably in this bin you have 5, in that bin you have 0, in that bin you have 20, then you divide the height by 100. In that case, it seems it's like a kind of probability mass function over a discrete random variable. However, you don't do that. That is one way. The other is that you also consider the width of each bin. So what you do is that you multiply height times width and sum up becomes 1, something like that. So you further actually divide the height by the width. In that case, you can get some function. If your bin is very, very small and your instantiation, your independent generation of samples is very large, then you sometimes have a very smooth curve. And the limit of that curve, in some sense, is what? The probability density function. Got it? So never forget that idea. By the way, last time I differentiated not to a derivative. I just distinguish it to notion of mixed random variable and mixture random variable. Okay? Mixed random variable is what? Mixed random variable has a CDF. Be careful. We use CDF to define what is a discrete random variable, what is a continuous random variable, what is a mixed random variable. If the CDF is a continuous function, the random variable is a continuous random variable. If a CDF is piecewise constant function, then it's a discrete random variable. If it is piecewise continuous function with only jump discontinuities, then it is a mixed random variable. I believe I didn't give you any example of mixed random variable. For example, it's like this. Suppose your random variable has PDF like this. So at the origin, you have direct delta with height 0.5. And in other region, you have a smooth function curve, for example, a Gaussian curve, but it integrates to 0.5. In that case, what do you have? With probability 1/2, you got 0. With probability 0.5, you have some random variable. Got it? So in that case, what happens if you compute the CDF? As I told you, something like this. Got it? So this difference is 0.5. So as I just told you, a mixed random variable is piecewise continuous with jump discontinuity. At the location of jump in the PDF, you have a delta function. Anyway, and then we can easily extend our notion of CDF, PDF, PMF to conditional CDF, conditional PMF, and conditional PDF. Once we define conditional something, then there follows what? 3 theorems. What was that in our probability part? First, total something. In this case, total probability theorem for CDF, PDF, and PMF. And then Bayes theorem. And then notion of independence. Okay. Anyway, those are important. And here, while we do conditioning, I emphasized something strange like this. So we consider an event that has probability 0. However, if we take a small interval, then suppose its probability is not 0. In that case, point conditioning does matter. And what do you have? As you see in the homework problem, sometimes you can have something like this. For example, X is normal with 0 mean and variance 1, and you want to find the conditional density of Gaussian random variable given the event that X squared equals 1, then suddenly you have delta functions, right? In that case, you may say that, wait a minute, the probability of this event is 0. How can I use it to define some conditional something? Of course, if it is a discrete random variable, you are right. However, in a continuous random variable case, point conditioning must be interpreted using, for example, histogram. So you have small bin with non-zero interval, okay? Because PDF itself is what? The kind of limit of some our intuitive thing, okay? Defined from or motivated from the histogram, a normalized version of the histogram. So here, delta method, the reason is that the people love use delta. Sometimes they use epsilon, but anyway, so delta method is very, very useful. And delta method, you've seen in your calculus of high school, right? You divide the interval into length delta, and you let delta tend to 0 and to get some nice formula, something like that. Okay, anyway, so we've done about the random variable, and today we are going to study transformation of a random variable. Here are 2 topics mainly. One is so-called expected value. Expected value is a transformation of random variable because it's like this. See that? Suppose you have an underlying probability space and a function, a random variable. And then given that you get some number. So this box transforms this triplet together with this random variable into some number, a real number. So I'm going to interpret an expectation of a random variable as a representative value of something. What is a representative value of something? Suppose you have some object that has shape, color, and some details. However, you want to represent it using a real number. How? Sometimes you want to represent it by using its weight, right? Sometimes you want to represent it by its height, depending on your goal or objective or your use, right? So you suddenly realize that given anything, we can assign a number. For example, you have your student number, even though you have brain, hairs, but you are represented by a single number, right? So a representative number is a very interesting idea and has been used by our human being for a long time after the invention of possibly the notion of number, right? And when I was an elementary school student, since we were so many students in a class, our teacher couldn't memorize all the names, especially at this first week or second week. He or she just called us as a number. And I still remember my first number when I was an elementary school student. And interestingly, there were more than 70 students in a class. Can you believe that? And now, probably 7 in class. Amazing. Yeah. Anyway, so I'm going to talk more about this representative number or representative value. Okay. And in terms of that, I'm going to talk about expected value. Okay. Anyway, and then I'm going to talk about transformation of a random variable as what? As something like this. Since we are electrical engineers, what do? We use systems which has input and output. Suppose we have a random variable here as the input of a system. And here goes a deterministic function g. Then let's call output as y and denote it as we usually do, something like this. If x and y are deterministic, then we call y equals gx. Similarly, let's denote it this way. And our question is that given the, for example, CDF of x and the shape of function g, what is the CDF of the random variable y? Sometimes, if that's too complicated to compute, what we ask is that, given this and that, what is the kind of moments that are special expected values or representative values of the random variable of y, something like that. So we have 2 topics. First, expectation. Second, moments. There are a lot of subtopics which we want to cover. So let's take a look at this thing. Actually, this part especially is half omitted even in my undergraduate course. So suppose that you have a multiset. Multiset is not fully adopted terminology in mathematics, but some people really love to use it. And you learned in your not elementary, probably high school math, suppose you have something like this. Then actually this set is equal to that set, because in the notion of set, duplication is not allowed. Order is not important. And if it is duplicate, you just drop that. In a set, you can say that, but if it is a multiset, then these 2 multisets are different multisets, because a multiset is allowed to have duplicate elements. Got it? So now, suppose you are given a multiset. I correct this one, okay, this morning. A multiset, some Sx, S sub x, and of real numbers here, important thing, with a common unit. Okay? Probably you remember when you are in elementary school at this time, you want to boast off your math skills. So you ask your friend, hey, what is 1 plus 1? 2. And what is 1 plus 3? 4, something like that. Probably my daughter is also doing that right now. And some of the students know how to tease them. So they bring 2 cups and a bigger cup and say that, okay, here is 1 cup. Here is another cup. Let me pour it. 1 cup plus 1 cup is what? And 1 cup of water, something like that, right? So they say that 1 plus 1 is 1. What is wrong? Actually, when I was asked the question, I couldn't answer definitely. I could somewhat argue that it's absurd, but I could not, how say that, perfectly beat that argument. What is wrong? Here goes the argument. Unit. When you add 2 numbers, when you add real physical something using numbers, actually you have units in real world. So for example, 1 cup of 500 milliliter water and another cup of 500 milliliter water, if you even to pour, that is not what? 1 5 milliliter cup of water, right? That is 1 10 milliliter cup of water. So if the units are different, you cannot add them up, right? So it's like this. You cannot add 1 ton of iron and 1 meter of string. You can't do that, right? So what is important here is that you have a multiset of numbers with a common unit. So actually, number does not have a unit, but number is accompanied by a unit. So you'd better say that you have a multiset of real numbers accompanied by a common unit. Now, what can you do? What would be a good representative value or number? Of course, you can choose one of the numbers among the elements, or you can have some number that is not in the set. For example, suppose this one has -1 and +1. According to our arithmetic average notion, we choose some number that is not either of these. We choose 0, right? So here, be careful. Whenever we choose a representative number or value, actually, we have a kind of universal set where our multiset is a member. Got it? So we assume there is some bigger number, real number. And we have a set consisting of 1 and -1. As a representative number, we can even choose some number out of this group. And actually, we have done in many, many times, right? For example, suppose you have 1 and 2. What is the mean? What is the average? 1.5, right? Anyway, so the first thing is that whenever you talk about a representative value or number, you have to keep it in your mind. Do they have a common unit? Otherwise, any number does not make any sense. Okay? No number can make any sense. Second one is that the representative number cannot be or may not be a member of this multiset. That is also very important. Some representative number is intentionally chosen from among the members of this multiset, but some representative values do not do that. Okay? Among representative values, you've seen some group of representative numbers called mean, median, mode. Probably you remember, right? They are all measure kind of central tendency of these elements of a multiset. Others sometimes minimum, maximum, and standard deviation. Sometimes you already know that's why I'm using it before defining it. They are some other very popular representative values. One commonality is that except very, very special case, no representative value fully represents the members. Got it? As in our politics, we are going to select representatives who is going to attend our National Assembly probably next month. Yeah. However, you have to admit that no representative can fully represent us, right? Because we are many and he or she is only one person. That is one of the reasons. So we lose some information. This loss of information is very, very important notion. Okay? Interestingly, some collection can be represented by only a few numbers. That is kind of called parameterized models or parameterized sets. However, in most of the cases or in general, we lose some information when we choose representative numbers. For example, here is a 5 numbers whose arithmetic average is 3.5. Here is same size, so number of elements are the same, and having the arithmetic average 3.5. Are they the same set? We don't know, right? Because the first set may consisting of 1 to 6, and the other set may consisting of all 3.56 times, right? So we lose information whenever you replace the entire set or something by using a single number. So what we do is that we carefully select to make each representative number really represent some specific character or characteristic of the set. Got it? Sometimes it's central tendency, sometimes it's dispersiveness, something like that. By the way, it's just for your interest. There is a QM, AM, GM, HM inequality. Probably in your high school math, you remember arithmetic and geometric mean inequalities. Actually, there is a version of extension of it. Quadratic mean, arithmetic mean, geometric mean, harmonic mean inequalities. So you go to Wikipedia and read it, okay? Anyway, mean, what I want to say is that the term mean is sometimes replaced by average. And unfortunately, they have a little bit different meaning. However, we mostly just use them interchangeably. Sometimes I will say mean to mean average. I will use average to mean mean. Got it? Anyway, so here goes something interesting. Suppose we have a random variable with underlying probability space. The reason why I and many people saying underlying is that as you learned in your undergraduate course, a random variable is fully characterized by a CDF or PDF PMF. In that case, as I told you, we don't need this hidden box. We don't know what we have, right? Sometimes we can generate the same random variable by choosing different set, different pair of the probability space and random variable. They may have same thing, as we will see in the transformation of random variable. For example, we have a uniform random variable generator. And then we have just take that output, pass through identity system and get, for example, x1. That is uniform random variable. Now we take it and take 1 minus x to have another one. That is also uniform random variable. So sometimes, even though for completeness, we have to assume there is a probability space, we don't care. In that case, usually we say that it's an underlying. It's like lying under, right? It's hidden probability space. Okay. So anyway, for perfectness or completeness, just say that we have a probability space and random variable. And my question is, what would be a good representative value? And one of the method is this. As I told you in the review of today's course, we want or we assume repeatability. So we generate many independent samples from a random number generator. And then what do? We construct a multiset and take, for example, the arithmetic average of these numbers. And what we do is that we take very large number of them that really appeals to our frequency interpretation of the random probability, right? And also, as you were taught in some of undergraduate courses, it is the idea of the law of large numbers. In the law of large numbers, we have what? Arithmetic average converges to our statistical average or expected value of a random variable. Anyway, so we may just generate many instantiations by independently combining the given random experiment as sub-experiments and compute the arithmetic mean. However, is that the only way to find a representative value? No, because we were taught in our undergraduate physics course about the center of gravity or center of mass. And what is it? Suppose first we start from discrete mass case, okay? Or point mass cases. Suppose your system has finite number of point masses located in one dimension with different masses m sub I. Its location is x sub I. What is the center of mass of that system? And you already know x bar, which is a single number that represents the entire point masses with possibly different locations and mass values, like this. But we do not stop here because we want to make a link between the center of mass and the expected value of a random variable. So let's see this. So let's group this total mass as capital M and put it in the numerator by dividing m sub I by capital M. Then what is it? Sum of m sub I divided by capital M is 1, right? So it's kind of normalized mass. And it reminds us something, right? Of something. It looks very similar to what? The probability mass. Because probability mass is a kind of mass, as we say, but they are always non-negative and sums up to 1. And now, in our definition of center of gravity or mass, we have what? This term. And it corresponds to our probability mass or our discrete random variable. Similarly, in our undergraduate physics, we had its counterpart for distributed mass. So suppose you have density function, mass density of rho of x. Here, the mass density, F, it integrates over the entire real line. It becomes the entire mass capital M. So what we do is that we similarly, here is a typo. There shouldn't be x. Sorry about that. So in the denominator, we have again capital M. So we move it to the numerator and divide rho of x. So here we have rho of x divided by m. Now it's kind of normalized version of the density, which is always non-negative and integrates to 1. Is it similar to our probability density function? Yes. So here goes our friendly definition, as you've seen in the undergraduate probability and random variables course. Suppose your x is a discrete random variable, then our expected value, in order to compute the expected value, we don't need to generate that. Actually, we are going to link between this and that idea of arithmetic average by using the law of large numbers, but not yet. Okay. Anyway, so let's take a look at this. I asked you to focus on a unit, okay? Because we too much take math courses, not physics or chemistry courses that have units. That's, I believe, one of the problem in electrical engineering. We rarely think about units. But see that? Suppose your real number is actually your random variable is accompanied by a unit. Then your representative number may have the same unit, okay? Especially in this case. For example, suppose you have a distributed mass, discrete mass on this, and its location is in meters. X1 meter, X2 meter, X3 meter, and M1 kilogram, M2 kilogram, M3 kilogram. Now, your center of mass must be what? Must have the unit of meters, right? Because you want to know which location is a representative location of these masses, right? Same thing in the average. See that? Suppose X says unit in meters, then your expected value, see that, has meters in the unit. Okay? So it's kind of value times normalized mass, value times probability. So value times probability, value possibly with unit times probability summed over the entire real line becomes the representative value. And same thing here. Here you have X probably having accompanied by a unit times density summed over. Whenever you see integration, if it is difficult to understand, just divide the interval and approximate it using a sum of many, many terms. It's okay. So actually, they are almost the same meaning. By the way, this was the undergraduate version, and here goes the graduate version, which perplexes you in many cases. So this is the definition of expected value. Here, what we use is what? We use the random variable as a mapping rule and our probability measure of the original underlying probability space. So here we have SEP and X of S, okay? And see that this is what? This is unit of same value as the output, right? So value times what is this one? This is a kind of derivative. We don't know how to define it, but anyway, this is kind of whenever you have in the S space, this integration also needs to approximate it by sum of partitioned space of the entire sample space, and you choose some center value S sub I, and you multiply the probability of the event that S is inside this event. So we can maybe write it this way: sigma I X Si, probability of Si is some AI. Got it? So I wrote this way and used decide to use gray because it's not precise, mathematically correct, but very, very good for our intuition. See that? Expected value of random variable X is what? We partition, as I told you, we partition the entire sample space into countable set, right? Non-overlapping. And we find the kind of value, single value, capital X of S sub I inside the ice partition. And then find the probability that S is in the event AI. So probability of AI, something like that. Value times probability. In Korean, 값 곱하기 확률. If 값 곱하기 확률 is summed, then whenever you see something like that, you must view it as what? Expected value. That's what I want to say. By the way, here it's a little bit over the our scope, but this integration is no longer your Riemann sense integration. Here goes the Lebesgue sense integration, but first thing is that even before we talk about our function needs to be represented by this formula. Probably you've seen in your undergraduate signal gen systems that any real valued function, f of x, let's say, can be written this way, or your high school math, right? This is so-called the even part of the function f. This is the odd part of the function f, right? So sometimes by defining something interesting, very simple, we can rewrite a given function as a sum of two functions, each of which has very interesting property. In this case, it's kind of even-odd decomposition of a function. We can do similar thing for square matrix. As you've seen, by using the transposition, you could do this, right? And here, what is this one? Symmetric part of square matrix A, of real numbers. Skew symmetric or anti-symmetric part of a square matrix, something like that. There are many something parallel like this. Among them is this one. This is very simple. Let me just give you in our friendly f of x thing. So suppose you have some function like this, its graph. Then what is its positive part? This one. So this gray line is f plus of x. Now, you are left the negative part, and what you do is that you reflect that like this. So this blue one is x, f negative x. So both f positive and f negative are non-negative functions. That's why you have a negative sign here. Got it? So they are all non-negative valued functions. You can do any time, right? And interestingly, in order to define x plus and x minus, you can use so-called max something with 0, or you can use something plus absolute value of it divided by 2, or recently in our AI course, you can use the rectified linear unit, and they do what? They do something like this, right? So here is the rectified linear unit. If x goes in, what is y? What is y? Y is value of x defined as something like that, or max x0. Got it? Same thing. They are all same thing. Okay. Anyway, why do we this? Why do we do this? It's because of the definition of summability. Okay. Suppose you have countably infinite number of real numbers. And what is the sum of these real numbers? When you are a high school student, what you did was like this. You construct a sequence of real numbers. And what you do is that you consider a partial sum from the first term to nth term. And then you consider the limit of that one, right? However, that is one particular definition, okay? Because in that case, you do not allow reordering of these terms. And what mathematicians have found in 17th century or 18th century is that even though you have countably infinite, not just uncountably, countably infinite number of real numbers with plus sign and minus sign, if both terms have infinite terms, for example, infinite number of positive terms and infinite number of negative terms, by reordering them and performing sequential sum, you can make the limit of the sum to arbitrary number. That's what people have found. So adding up finite number of real numbers is fixed under any rearrangement. However, if you have infinite number, then you have a problem. What is good is that when you have the same signed numbers, for example, you have infinite number of positive numbers, then rearrangement, reordering doesn't matter. If you have all negative numbers, reordering doesn't matter. If single sequence converges, then any rearrangement converges to the same limit. If that blows up, then every sequence blows. So what people have done is this. Since I told you integration is a what? Good approximation or mathematical refinement of some of many, many terms, right? Sometimes we have to divide our entire real line into countably infinite number of small intervals. And then for integration of a function, we multiply what? The width and height and summed up. Sometimes each product of width and height may be positive, sometimes negative. So in general case, we have countably infinite number of positive terms and countably infinite number of negative terms. And then our sum is not well defined in general case. So what we do is this: to circumvent that problem, we select positive numbers only and compute the sum of that. We choose negative numbers only and compute the sum of that. And then if both of them are finite, then we say that the integral is well defined. Right? That's why even though we just say that the expected value of x can be written in this way, it confuses a lot. It could be better rewritten in this form. So what we do is that we compute the expected value of the random variable by taking positive part, and then negative part, and if they both converge to finite number. If both of them are finite numbers, and then we subtract them and call it the expected number. What does that mean? Sometimes, given a random variable, this is very important, given a random variable, the expected value may not exist. And it may surprise you because many textbooks, undergraduate textbooks, makes a wrong statement. Suppose you have something like this. The density function is given this way. So let me give you a graph. So it looks very similar to the bell-shaped curve of Gaussian density, but actually it's a polynomial function in the denominator. So it has very heavy tail. It slowly goes to 0 compared to light-tailed Gaussian. Now, what happens? What happens? Suppose we want to compute the mean value of this Cauchy random variable. You may say that, okay, it's symmetrical. Its mean must be 1, right? That's what you learn. And even our undergraduate book has that. Given a symmetric PDF of a random variable, mean is the point of symmetry. That is not correct, okay? That must be stated in this way. If that random variable has the expected value, then, so existence, if assumed, then point of symmetry of the density function becomes the mean. However, mean may not exist. And let's see what happens. So here, in order to compute the expected value, you have to do this. X times 1 over pi, 1 plus x squared. Now, this x makes half of the values negative. So what you want to do is that you take the positive part, right? And the negative part. Let me, not this one. Something like this. Am I right? Right? Because x so actually, after change of variable, what you can see is that this is 2 times integral 0 from infinity, x divided by pi 1 plus x squared dx, and this goes to infinity. Okay? So actually, you have infinity minus infinity, and you may say that they are the same 0. But it's not true. Okay? Mathematicians don't do that. They say that mean does not exist. So it's not infinity. It says that mean does not exist. For the Cauchy random variable. But for Gaussian, as you can see, you can show that the point of symmetry is simply the expected value. Anyway, so the last comment is about the Lebesgue integral. And what is the integration in your high school and elementary calculus in undergraduate program? That integrations, those integrations were all Riemann integrations. What does that mean by Riemann integration? Riemann integration is motivated by this idea. Suppose you just want to compute the expectation of f from some interval a to b. And on that interval, function value is have the same, this is important, have the same sign. Then it corresponds to the area, actually. That motivates us the notion of integration. In order to calculate the area of this shaded part, there are many, many ways to divide this shaded area into small ones whose sub-area is easy to compute. Among many, many possible ways, right? Because this can be divided into any way. Riemann integration divides this area into strips whose sides are parallel to y-axis. That is Riemann integration. And what is the Lebesgue integration? Lebesgue integration can be just, I'm not saying that, I'm not precisely state, can be thought that you divide into strips whose sides are parallel to x-axis. Think in that way, okay? But it's not precisely like that, okay? So what you do is this. So that's the difference, and let me continue. So here is our part, and what you do is different. So you may say that, okay, according to professor's statement, I divide into this way, but actually it is not. You just draw the lines like this, okay? And what you do is that for each bin on the y-axis, you find the representative value. For example, here, this one. And then you try to find the length of x-axis, okay? So it's like you first choose this value, dividing the interval here on the y-axis. Because maybe this is not a good idea, so let me draw a different one. Suppose you have function like this, okay? A and b. Now you divide this way. Now for this interval, you have these 2 points. And these 2 intervals. What you do is that you, of course, find this y sub I, right? And then you find the length of this one. You find the length of that one and multiply and sum over. Okay, got it? That is Lebesgue integral. So it's not precisely dividing this one into y-axis, because if that is correct, Lebesgue integral is just x and y interchanged and Riemann integration. That's not, okay? So the idea is that you divide the y-axis and then find the length of interval that has this value, okay? When you compute this interval, so-called the measure of the size of this interval kicks in. That's why Lebesgue integration is often called that the integration for measure theory. Okay? Anyway, what you need to remember is this, even though I didn't state it here. If given an integration, you want to calculate some area, right, of a function enclosed by x and parallel lines, then if your Riemann integral exists, that has the same value as its Lebesgue integration. That's why in most of the cases, not strange cases, you can rely on your friendly old friend Riemann integration. However, in some strange cases where Riemann integral does not work, you need to resort to the Lebesgue integration. Here goes the example. This is one of the representative examples. Suppose you have a function f of x defined on the interval 0, 1, and that is 1 when x is irrational, and 0, 1 interval, and it's rational. Now, I ask you to compute the integration of this function. First, in the Riemann sense, 2 in the Lebesgue sense. What do you do? In the Riemann sense, what you do is that you divide the x-axis into subintervals. So let me do this. And what you do is that for each interval, right, you find what would be the maximum and the minimum, right? Because you want to compute the upper Riemann sum and lower Riemann sum and take the limit of them. And if the limits are the same, then you call it the Riemann integral. What's the problem? Whenever you have a small interval of non-zero length, the minimum value is 0 and maximum value is 1, because there are infinitely many real numbers and rational numbers and irrational numbers, right? So lower Riemann sum is 0. Upper Riemann sum is 1. They never coincide, right? So Riemann integral does not exist. However, now let's do it for the Lebesgue integration. So what you do is that you divide it into these strips. And now, especially for this strip, which has value 1, right? So y value is 1. What you want to find is this. You want to say that because all the other intervals has no occurrences of these values, this Lebesgue integral must be 1 times size of x such that f of x equals 1. Now, what is that? Size of what? Irrational number in this interval, right? What is the size of irrational number on this interval? In the measure theory, they say it's 1. What is the size of rational numbers in that interval? 0. Okay? And Google it or YouTube it. Got it? If you have interest. Anyway, so it's 1. Got it? One of the most important concepts you have to learn in this course is that the difference between finite set and countable set and uncountable set. Whenever you have a finite set or countable set, its length is 0. Okay? So what? Set of rational numbers has length 0. So in the entire real line, the set of rational numbers has length 0. So it's part of it has also length 0. Got it? Anyway, here goes the graduate version of expected value. And you may say that, okay, I know what? Because here goes what? Value times d capital F. What was that? CDF of x. As I told you, as far as we are given the CDF of a random variable, we have fully characterized the random variable, right? So if the major theoretic version of expectation must be defined using the Lebesgue integral of what? X times x of s times dp of s. That looks odd. We must be able to define the expected value of a random variable in terms of the equivalent thing. For example, the induced probability measure. However, that induced probability measure is equivalent to the CDF. So here goes the expression. You rarely see. However, some of your undergrad physics textbook had that when they defined the center of mass. They had that one because they didn't want to separate the discrete mass system or continuous mass system. They wanted to rewrite it in a single form. Same thing. If we use the CDF, we can write it in a single form. And let's take a look at this one. This is a summation of what? Same thing, just consider in the Riemann way. So you divide the x-axis into several things, and you find the representative value at each interval x sub I, right? And what? What is this one? Whenever you see d something, replace it delta of something, which is something minus something, little bit offset it. So it's like xi, right? But this is actually fx xi plus some delta I minus fx xi, right? So this d something must be interpreted as the difference of that one, right? That is your lesson of calculus, right? Actually, that is motivates the notation, right? Integral f of x dx. What does it mean? Summation of f of xi delta sub I. What is delta sub I? xi plus 1 minus xi. So difference of x. Same thing. Difference of capital F. What is that? Probability, right? Of event that x is in between these two numbers. So that is exactly what? The probability of x p sub I. So value times probability summed over. Got it? One good thing of this definition is that it applies to every random variable, because CDF is always defined for any random variable. But be careful. Here, I sometimes show that one in the note, but does not. But you have to be careful. I'm assuming that there is no point mass at plus infinity or minus infinity. If you have that case, because sometimes that is very important in your mathematical modeling, be careful simply doing integration, differentiation as you've done. Because think about this. Whenever we have integration, if that exists, actually, that integration from negative infinity to positive infinity must be same as what? Integration from sufficiently small number to sufficiently large number. But the problem is that if we allow real infinity as a number, no finite number can reach that infinity. So we omit some probability. That is very dangerous. So whenever you model mathematically a system, if you want to circumvent any trouble, just never allow point mass in plus or minus infinity, but just let them have very, very absurdly large number. For example, suppose you build an electrical system with all the values confined to plus minus 5 volts. Then, if you want to assign some plus infinity, let it have million volts. Got it? No infinity. Of course, this will be forgotten by you because it's likely that you will never see this kind of situation in your entire engineering life. However, nobody knows, right? You may have picked that EECE574 lottery last week in the Seoul Kepo area, right? Anyway, so here goes the properties of expectation. And actually, I also want to say a lot about this because this is one of the most confusing part, actually. See that? Suppose you have random variable x and y. What? Two random variables? Is that the topic of next chapter? Of course, you are right. However, one interesting thing is like this. Suppose you are given one probability space and two measurable functions. They both map the common sample space to real line. It's possible, right? Simply just draw a block and you have an outcome and two branches. Since we are electrical engineers, this is not that difficult. This is x of s. This is y of s, right? Simple. Now, what is this one? Let's use our measure theoretic definition. Then what? A times xs plus bys dps. That's in samples. And this integration is linear operator. So what? We have which is a expected value of x plus b expected value of y. So we have the linearity. We don't need joint CDF or anything, okay? Right? We don't need joint PDF, CDF of x and y. If we rely on our measure theoretic definition of expectation. See that? Here goes the common probability measure P, because there is single probability space with probability measure. If you show this without using that definition, then what? You have to somehow define joint CDF, PDF, PMF of x and y. We don't need that. That's what I want to say. Okay? And there goes very simple things. Expectation of a constant number is constant. Too obvious. For the later parts, I will talk about it on Thursday. It seems that I'm very slow in covering. I hope to cover all of the topics. But it seems I just covered half of them only. Less than half. Okay. But anyway, I believe you enjoyed today's lecture and you are very motivated to study a little bit of Lebesgue integration. Got it? Okay. That's all for today.